Hello, my name is Yan Vugenfirer, and I'm a CEO at Daynix and a contractor at Red Hat. Here with me is Yansu Li, Principal Software Engineer at Oracle. Together, we are going to talk about implementing SR-IOV Failover for Windows guests during the migration. So during our presentation, we are going to discuss Virtio-net drivers in general and give you some overview on the Virtio-net drivers. We will talk about some Windows guest terminology for the people that are less aware of it, discuss the problem with the SR-IOV migration, go about a little bit overview about different solutions, and then we will discuss our solution. So let's talk about Virtio-net drivers first. So here we have a link to the GitHub where there is our Upstream repository. And in this repository, you can find all the major drivers, all the major Virtio drivers. We have a Virtio-net, Virtio-block, Virtio-SCSI, and other drivers. In this directory as well, there are some other guest drivers that are not related to Virtio, like Panic driver and firmware config. And also some INF files that help us to define the system. For example, SMBus INF for a Q35 chipset or PCI serial. So what are those drivers and how they are built? So the network and the storage driver, they are built in the architecture, Microsoft architecture called mini-port drivers. So each in their respected driver technology. For network, it's NDIS, and for storage, it's store port or SCSI port. And other drivers are WDF drivers. So it's a Microsoft framework that allows you to easily write kernel drivers. What are the supported OSs? So we support all the OSs starting from Windows XP up to Windows 10, and same with Windows servers, 2003 to 2019. From the Windows, for Windows 10, we also support ARM64 platform. How can you contribute? So please send pull requests. The code changes should pass Microsoft certifications, but don't worry, we are running CI on the upstream, so you're covered for that. And who were the contributors for the project during the years? So main contributors are coming from Red Hat, but we had also contributions from Virtuoso, Oracle, Google, Microsoft, AWS, and others. So now let's talk about Windows terms and how the network driver architecture looks like in Windows. So you'll hear a lot during this presentation, NDIS. So what is NDIS? It's a network driver interface specification. It's also ABI for network drivers. It's also the architecture of the network drivers in kernel. And there is NDIS.sys, which is a Microsoft driver that you can see in Windows kernel, and it implements part of the NDIS functionality. So if you will go from bottom to top, in the bottom, you will see hardware devices, and on top of them, there is a mini-port driver that usually supplied by the vendor, and this driver drives the specific device. In the simple case that you can see from the right side, there are binded protocol drivers just on top of the mini-port driver. The more complicated case is when we have also intermediate driver, and then the protocol drivers are binding to the intermediate driver. So intermediate drivers towards the mini-port driver have ABI of the protocol drivers. So mini-port thinks that it talks to protocol driver, and towards the protocol driver, it has a mini-port ABI. So protocol drivers think that they talk to mini-port driver. Why do we need such a thing? So one of the examples is the MUX driver that can sit on top of several mini-port drivers and present one virtual NIC to the top layers. Also in the user space, we have notify object. Notify object can get callbacks from the network configuration subsystem and act on those callbacks by changing network configuration, removing drivers, installing drivers, etc. So how the Virtual-net or NetKVM driver for Windows looks like. So it's NDIS mini-port driver, as we mentioned before. And the basic driver package looks like you have the INF file, which is an installation descriptor. You have a sys file, which is a driver binary. You have a PDF file. Those are symbols for debugging. And CAD file, which is the package digital signature. So now let's discuss the problem, why we even needed to do something. So when we are talking about para-virtualized devices and drivers and or fully emulated devices, all the code resides inside of QEMU, and QEMU also controls the data path. So when we want to migrate such device, it's just migrated with virtual machine, all the device state is migrated, QEMU fully controls the data path, etc. But when we have external hardware device and QEMU does not control the data path, the DMA continues to run, we need somehow to migrate the hardware state, and therefore there are several solutions that were proposed over the years. So we will have a small overview about them. Some are more vendor specific. We'll talk about what Microsoft did in Hyper-V, and there's a solution in Linux with 3-net dev model. So regarding previous effort, I think almost every year on the KVM forum, we have at least one presentation about SR-IOV migration. So they're ranging between very vendor specific or device specific solutions to just now there's a parallel session about more generic solution. And now I am passing the presentation to Annie, and she's going to give the overview about the solutions that Microsoft did and about our solution.
Thanks, Ian. Hi, everyone. This is Annie from Oracle. Today, I'm going to talk about the software solutions of SR-IOV migration in Windows. So these solutions focus on switching data paths seamlessly between VF network and the Virtual network. Before initiating the live migration, the VF network adapter will be hard removed, and all network traffic will be redirected to the Virtual network data path. After the migration is done, the VF network adapter will be hard added on the target. So all the network data will go through the VF network path. Today, I will talk about the existing solutions. First, there are the Windows NIC Teaming, Windows Max Intermediate Driver, and Hyper-V solution. After that, I will talk about the 2-net dev model in Windows Virtual Driver. So the Windows NIC Teaming is built in Windows since Windows Server 2012. It is similar to the bound in Linux. And the Windows NIC Teaming provides the failover capability. User can put the Virtual network and the VF network into one team and configure the Virtual network as standby. So when the VF adapter is hard removed, the Windows NIC Teaming will set the Virtual adapter as active and switch the data path to the Virtual. After the VF adapter is hard added, the Windows NIC Teaming will set the Virtual adapter as standby, and then the data path will go through the VF adapter. So the Windows NIC Teaming can be configured through GUI or the PowerShell in the user space. However, we prefer the solution in kernel space to switch the data path automatically, and the user doesn't need to spend time or effort in configuring user space. So Windows Max Intermediate Driver is a kernel solution. It exposes one or more virtual adapters based on the relationship between the virtual adapter and underlying network adapter. It has the various models. Today, I only introduced the 1-to-2 driver model for the SR-IOV live migration. This model is similar to the NIC Teaming in failover mode. Its architecture is also similar to the 3-net dev model in Linux. So this slide shows the architecture of the 1-to-2 max driver model. As you can see, the bottom are the Virtual network and the VF function network. They have their own mini-pod driver serve them. That's the NetKVM driver and the VF mini-pod driver. On top of them, that's the 122 max intermediate driver. This max driver exposes the protocol driver as a lower edge to band to the underlying minipod driver. Also, expose the minipod driver as upper edge to band to the TCP/IP and other protocols. Inside the max driver, the minipod virtual adapter band to its own protocol driver internally, so the NDIS isn't aware of this banding. The max driver has full control on the network data here, so it can switch the data path between the NetKVM and the VF minipod driver. So the thing is, the underlying minipod driver exposes NDIS file banding interface. To avoid the confusion between the banding interface NDIS file with the NDIS version, so I will only use the term NDIS here. As you can see, the protocol driver in max driver exposes NDIS banding interface, as well as the TCP/IP and other protocols. This means this underlying minipod driver band to the max driver protocol, also band to the upper layer protocol. However, the max driver only want to expose the virtual adapter here, not the underlying minipod driver. So a notify object is involved here to unband the upper layer protocol driver from the underlying NetKVM and VF minipod driver. Here, I will skip the details about the notify object, and I will go into more depth on it later. So this snapshot shows the banding details of NIC Teaming on max driver. So they show the similar banding, so I only pasted one for both. So the Ethernet 14 and the Ethernet 5 are the VF and the Virtual network adapter connection. They only band to the network adapter multiplexer protocol. And the SR-IOV network connection is generated by the NIC Teaming or the max driver model. It bands to all necessary upper layer protocols, but it doesn't band to its own protocol driver. So as we know that Hyper-V supports the SR-IOV lab migration, so let's see how Hyper-V works. The important part of the VM network is the network virtual service client. That's the NetVIC. NetVIC also communicate with the network virtual service provider through the VM bus in parent partition. So that's the synthetic data path. The NetVIC driver also communicate with the VF minipod driver for the SR-IOV lab migration. And the NetVIC also provide two installation files. One is for installing the NetVIC minipod driver, another for installing the NetVIC protocol driver. Both two drivers share the same driver binary. Normally, their name are tagged with the NDIS version. For example, NetVIC 6.3. So let's see the architecture of Hyper-V SR-IOV VF failover. So as you can see, the VF minipod driver in Hyper-V exposes the banding interface upper range as the NDIS VF. And the NetVIC protocol driver is the only protocol driver that exposes the NDIS VF banding interface. So this means these two drivers can band together exclusively. And there's no notify object involved, neither no new virtual adapter is generated. Also, there's no band or teaming involved. So the NetVIC protocol driver sits in the same driver binary as the NetVIC minipod driver. So as you can see, because of this, it is possible for the protocol driver to access the network data from NetVIC minipod driver and forward them to the VF minipod driver binary reach the virtual function device and vice versa. So here is the network banding of Hyper-V. The Ethernet file is the VF network connection. It only bound to the NetVSC failover VF protocol driver. The Ethernet 4 is the Hyper-V virtual adapter connection. It bound to the TCP/IP and other protocols, but the Hyper-V failover VF protocol driver is hidden to it. So as we can see, the max driver model is complicated. A new virtual adapter is generated. This requires deployment of the new virtual mini-pod driver, and the offload have to be restored in the max driver. And also, the notify object in the max model is complicated. The installation involves installing the virtual adapter mini-pod driver, also the offload the protocol driver. So this means more efforts are required for the deployment of the max driver model. The Hyper-V model is simplified, but it is only appropriate for Hyper-V. In Linux, the mailbox mechanism is implemented for the VF and PF communication. However, different mechanism is implemented for the Hyper-V in Windows. As a result, same device, VF device are advertised by different device ID. And the Windows VF mini-pod driver end up with different implementations too, as well as the binding interface is posted differently. This means we cannot use the Hyper-V implementation directly in KVM. So here the question comes, what should we do for the SR-IOV lab migration in Windows guest in KVM? The idea here is to combine the max driver model and Hyper-V model solution together, and that's the 2NET dev model in Windows. So let's take a look at the regular network and virtual network and the virtual function network. They have their own mini-pod driver to serve them. That's the NetKVM and the VF mini-pod driver. These drivers band to the up-layer protocol directly. Let's see what's new in the 2NET dev model for the SR-IOV LAN migration. So a new virtual protocol driver is implemented here. It shares the same driver binary as the NetKVM mini-pod driver. So that's very convenient for them to share the data between them. Also, the VF mini-pod driver is post the binding interface NDIS here. As you can see, the virtual protocol driver and the up-layer TCP/IP other protocol also expose the NDIS binding interface. That means the virtual VF mini-pod driver bound to the virtual protocol driver, also bound to the TCP/IP other protocols. So a notify object is implemented here to guarantee the binding between virtual protocol and the VF mini-pod driver are in one-to-one mode. So the notify object is a COM object that sits in the dynamic link library. When the virtual protocol driver is being installed, the network transport class installer will register a notify object for this virtual protocol driver. So when the VF device is hot added, any new binding generated to the virtual protocol driver or the VF mini-pod driver will be detected. So if the binding is between the virtual protocol and the VF mini-pod, it will be allowed. Any other bindings bound to them will be disabled. So this guarantees the binding between the virtual protocol driver and the VF mini-pod driver are exclusive. So the protocol driver is the important part in the 2NET dev model. So I will talk about it in more details here. At first, the protocol driver behaved like a bridge between the miniport driver, Virtual miniport driver, and the VF miniport driver. And also in ToNet model, the VF adapter is coupled to the Virtual adapter with the same MAC address. When the VF adapter is hot added, the protocol driver will search for the matched MAC address among all existing Virtual network devices. If there's a matched one, the protocol driver will bind it to the VF miniport driver and switch the data path to it. So when the VF network adapter is hot removed, the protocol driver will shut down its binding and switch the data path back to the Virtual. For the TS network data, the protocol driver will set the source handle of the net buffer list as the VF miniport binding handle and forward the network data to the VF miniport through this handle. For the RX network data, the protocol driver will indicate all the network data from VF miniport to the upper layer protocol through the Virtual miniport handle. The object identifiers are wrapped and forwarded. Offload are propagated in this same way. And the work of the propagation in this case is much less than the restoring offload work in Max driver. So here is the binding details of the Virtual SR-IOV. The Ethernet 5 is the VF network. It only binds to the Red Hat Virtual NetKVM protocol driver. It doesn't bind to any other drivers. Ethernet 11 is the Virtual connection. It binds to the TCP IP other protocol, but it doesn't bind to its own protocol driver. So you can see that's now that you know how the ToNet dev model works in the Windows Virtual driver. So I will hand it over to Yan to talk about the current status of the ToNet dev model. Yan, please take it over. Thank you.
Thank you very much, Annie. So let's talk about the status and the known issues. So the code for this solution is already upstream and you can use it. And the known issues that we have are the following. So first of all, the support is only for the newer operating systems. Second, the statistics for the VF is missing because they are not propagated to the NetKVM driver. We have some issues that are related on the order of starting of the devices. So one of them is a DHCP issue that we might have. And another thing that you should know is that if you want the solution to work on the specific VF, you need to add the plug and play ID of this VF either to the notification object code or to the registry. Regarding the current solution with Virtio-net spec and NetFS standby, so we are not using this capability right now because we are relying on the notification object to notify us about the appearance and disappearance of the devices in the system. In the future, we might use it. Some changes in the installation. So first of all, what we had before, we had one INF file for the miniport driver. And after those changes, we have one INF file for the miniport driver, and we have another INF for the protocol driver definition and for the notify object. So it's kind of a dual installation here. Regarding WHQL certification. Before, we were certifying the miniport driver and the Microsoft automatically reviewed the test package. And currently, it's a two-step certification. So first, we need to verify the miniport driver, and there is automatic review for that. And then we should verify the whole solution and submit the test results. And it's a manual review for the second time. Let's take a look at the performance numbers. And here's the performance number on 100 gigabit per second card between the hosts, and you can see it a VM to remote host traffic. So there are several things. So first of all, what we wanted to see is there's almost no degradation between the usage of the VF and the usage of the 2NetDev model in our solution. And you can see it here. And in order to achieve it, what we had to do is, of course, to propagate the OIDs correctly in order to ensure that the offload is propagated correctly from offload settings are correctly propagated from the VF to the protocol driver, and also ensure the correct settings of the jumbo frames. So you see here MTU is 9,000. This is the data for remote host VM as well. You can see that the performance here is almost not diminished when we are using our solution. And another results are VM to VM that are running on remote hosts. So thank you very much. If you have more questions, please ask us in the chat or send us emails with questions and comments, and we'll be happy to answer them. Thank you very much.